So welcome and thank you for coming. I'm Heidi Stelzer. I'm a biology professor here at Fort Lewis College, and welcome to the forum on metals and sediments in the Animas River. We appreciate you guys coming out on a Friday night for a talk that will be filled with science, and hopefully science that you feel can help inform you for the ideas and understanding you want to have about the river system. Tonight we have scientists from the University of Colorado, from the USGS, from our community, and from our college joining us together so that we can understand more about the river system and the metals and the sediments that were deposited as part of the Gold King mine spill, but also have been present in our river system for a really long time. This forum is designed to be somewhat general in nature so that we can start to understand the context for what happened better, and we can understand the processes that take place in a river system in a high metals environment that will continue to impact us for the future, so we can understand the big picture rather than a small, narrow sliver in the picture. Many of us came to Durango, or were born here and chose to stay because of this area's natural beauty, including the Animas River and the Animas River Valley. The feeling on campus after the Gold King mine spill was to figure out ways that we could help our community, and one of the thoughts that we had was that we could work on ways of finding to share our knowledge. We teach our students on a regular basis, and this is an opportunity to share that same knowledge we've been sharing in our classrooms with students throughout the fall with a broader audience, including a lot of you who are working to manage for the river system and to make the choices that are hard ones to make to figure out what we do next. This forum is an opportunity for the Fort Lewis College, Durango, and other Four Corners and Colorado communities to gather together and learn about the science related to metals in the Animas River, and that should inform our decisions. And to begin with, I want to tell you an anecdotal or a story. Many of you may know this is my son. His name's Rowan, and this is a picture when he was 2. When he was 2 years old, we were living in Fort Collins in a house that was built in 1901. And Rowan liked to sit outside in the pickup truck in the driveway and stand at the steering wheel and pretend that he was driving. The truck door would be closed, and my husband and I both felt like he was pretty safe in there. He was 2. We didn't think he knew how to open the door. So it had rained. There were mud puddles in the driveway. He did know how to open the door. He opened the door, and he took a tumble. And the picture tells most of the rest of the story, which is that he landed face first in a pretty major mud puddle and then came into the house looking like this and was a little upset, but you can see he's not crying, so he was just more shocked than anything else. What you can't see in the picture, and what's often the case with environmental issues, is that you can't see the contaminants that were part of our driveway. The contaminants that are part of the dust and the dirt in our driveway, because we were living in a house that was built in 1901. There's an old single-car garage that looks more like a barn that was painted with lead paint, multiple layers and coats of lead paint. And when we first moved into the house, we'd asked about what we needed to do to plan for this old barn that we knew was covered in lead paint, and they said, don't do anything because it's not peeling that much. It's just peeling a little bit. So there's lead paint in the dirt and in the dust around our house, and we knew that. But in this case for Rowan, it was short-term exposure. So he fell, he was covered in mud, we brought him to the house, and he was cleaned up pretty quick. For many of us right now, we're grappling with questions and trying to understand what long-term exposure to metals looks like, learning that there's a greater complexity to what we now are aware of as a result of the Gold King mine spill. What we're trying to ask ourselves and gain knowledge from each other in our community is how will we know if the dirt can hurt us? And the dirt remains one of the key questions about the Gold King mine spill. So the Gold King mine spill brought attention to this issue, and tonight the panelists will begin sharing key concepts on metals and sediments. Where are they? How do they move in the environments? What's the chemistry by which they become available or unavailable so that they can do or not do harm to people? I'd like to now introduce Callie Cole. Oh, sorry, I forgot to read the part of the slide. So we live in a metals-rich environment, the rest of its notes. So we live in a metals-rich environment, and we're not the only region of Colorado that's metals-rich. And so this map shows you that there are other regions like ours that, because of the underlying geology of the mountains, there's concern for natural sources, not just anthropogenic and human-caused sources of metals in the environment. With that, I'd like to introduce my colleague, Callie Cole, who will be facilitating the set of panel speakers, and she'll tell you a little bit more about the format of this event.
Thank you, Heidi, for putting on this event and really making this happen tonight. Please join me in thanking her. Also, there are several panelists here, not just one. They're sitting down here so we can see each other's talks. But I'd really like to thank the panelists for being here tonight. So as Heidi said, I'm an analytical chemistry professor here. I just started this semester, and I've been working with Heidi to organize this event. Thank you all for being here tonight and participating in a community discussion of something that has impacted all of us, but is really science-based. So it's important for us to see all the data that's out there and really talk to each other about it. I'd also like to thank the sponsors of this event, the University of Colorado Office of Outreach and Engagement, the San Juan Basin Health Department, the Department of Energy, the U.S. Geological Survey, and of course, Fort Lewis College. The organization of this event will start with 10-minute-ish presentations from each panel member. They'll talk about some of their most recent data, and then we're going to open it up to a discussion and a Q&A, where we're going to use these two microphones up here and hopefully form two lines. And if not, I'll be running around with the mic, putting it in your face. Hopefully you'll ask a question. So without further ado, I'd like to introduce our first panelist, which is Joseph Ryan, a professor of civil, environmental, and architectural engineering, who is visiting us from the University of Colorado at Boulder. So please join me in welcoming Joseph Ryan.
Good to see you all. I'm glad I'm here in Durango, down here from Boulder. Lived in Boulder for about 20-some years. Before that, I grew up in New Jersey, and I told the student group this morning one of the reasons I got interested in environmental engineering, that's my thing, at the University of Colorado Boulder, was the opportunity to go to a geology field camp. And there was some mining involved and that sort of thing too, but not too much mining in New Jersey. When I did finally get out to Colorado, I realized that for about, I don't know, 8 or 10 years, I had been driving by a bunch of abandoned mines and never really noticed it. And finally, our community, Jamestown, Colorado, which if any of you paid attention to the flooding that happened in the Front Range a couple of years ago, Jamestown was one of the towns that was hit quite hard by the flooding. Jamestown had some issues. They wanted to build a new tennis court, and it was on top of an old tailings pond that a lot of people didn't realize, and they weren't allowed to build it then. So we got involved through our university's outreach organization in helping to try to figure out what kind of mining legacy there was in what you see on the screen here, the foothills west of Boulder, Colorado. You see Boulder down at the bottom there. You see some colors on this thing. The colors are showing different watersheds that the city of Boulder uses as drinking water sources. And one of those, where you see a lot of those mining symbols, is actually a water supply that comes down to a utility called the Left-Hand Water District. That if you live outside of the city of Boulder, there's a good chance you get your water from Left-Hand Water District. You can see there's quite a legacy of abandoned mines up in that part of Colorado. It's sort of the northeast end of the Colorado mineral belt that Heidi had on her slide. And there was gold mining primarily, but later there were some other interesting things mined. Fluorite, calcium fluoride, which during World War II was mined primarily because of the fluoride was used in soldering flux. But later it was mined because fluoride was determined to be useful in toothpaste. So that was one of the sources of fluoride going back a ways. There were water quality issues noticed and that had been persisting for quite a long time, but various events came together and some money became available, but there wasn't, everybody realized there wasn't enough money to figure out exactly how to clean up all of these different sites, so it was a question of priorities, and that's where we got involved. My students and I risked our lives to collect some samples from the Left Hand Creek watershed and did a bunch of studies that one of our following speakers, Rob Runkle, had been involved with quite a bit with the U.S. Geological Survey, these things called metal loading tracer tests. Not just to measure the concentrations of the metals that were present in certain areas, but also to multiply that by how much flow there is. So some little stream with a lot of metals could be just as much of a problem as a big stream with not much metal. You still might have the same amount of metal moving down the watershed in each one. And we came up with some results that might have looked like this. And what I've got on the y-axis here is the copper loading rate, how much copper is going down the stream. And on the x-axis is distance, and that's in meters. So each 1,000 there would be a kilometer. And that's overall, that's about a 4-mile reach of a river. And the dots you see on the graph, we've got these things called total and dissolved copper. And the total is a water sample that you just measure how much copper's in it without doing anything. And the dissolved is you put it through a filter and only measure what gets through the filter. And I'll come back to that in a second. And the orange line on the bottom was the detection limit for what we could measure. So you could see in some cases there wasn't much copper there. But in other cases there were some peaks. And the big advantage of this technique is you can go and look at, well, what might have caused some of those peaks? And in one case it was an old mine, this one that, where they had the calcium fluoride. In another case there was this rather odd site where it was called Curie Springs, like in Madame Curie. They used to get uranium-rich radioactive water out and sell it as a health water. I'm serious. This was in the 1960s. They eventually got shut down by Boulder County Department of Health. Further downstream, there was another mine called the Golden Age mine that was, you could correlate its input to what you saw in the stream. And with that kind of data, we could figure out how to spend this money. And so, you know, I've got these dollar signs distributed around some of these mines. Some of them were cleaned up. Some of them are still in progress. Some of them, a lot of money was spent, a few millions of dollars in a Superfund site right near a little town called Ward. Some of them were a couple $100,000. Some of them were a few tens of thousands. It all ended up improving the watershed in a way that we want to document better in the future, but at least qualitatively, we, well, to some extent quantitatively, know some improvement was made. So some of the speakers who come after me will talk a little bit about what's going on down here and what had gone on down here in the Animas. And one of the big issues, of course, was you know, the river was orange. And you know, I was teaching water chemistry this semester, or leading into it, shortly after this spill occurred. And it was a great opportunity to teach the students a few things right off the bat. To what extent, what effect did those orange particles have, those iron oxide particles? So you take some toxic metal, potentially toxic metal like copper, they're going to adsorb rather extensively to the iron oxides, and in that case, not much of them would necessarily get into the fish. When you filter that water, a lot of those iron oxide particles get caught on the filter, and some of the dissolved copper comes through, and that's what we should really be worried about in terms of affecting aquatic life. It was interesting in looking through some of the data that was generated early on that only the total copper was, total metals were measured, and I couldn't quite use this example until later when some of the dissolved samples were also, or the filtered samples were also presented in some of the data. So that orange stuff in the water was rather protective to the fish, at least early on. You know, one other thing to think about in terms of fish and human health is we don't live in the water. If you do a risk assessment, we drink a couple liters a day. And copper is a good example of the big contrast here. The standard for aquatic life might be something like 13 parts per billion, depending on the hardness. For humans, drinking a couple of liters of water, it's like 1,300 parts per billion. So things that we think of as a risk to humans are potentially much bigger effect on aquatic life. Now, the one other thing that you'll see as the next couple of speakers come up is what happened to all that orange stuff, all those iron oxide particles as they moved through the water. Some of them settled out. We know a lot of it ended up on the sediment at the bottom of the stream. And the big question now is to what extent might any of those toxic compounds come back out, whether it's in the particle form or in the dissolved form. And this is, I would say, one of the things that we are not great at predicting or assessing. We have some ideas, we could make some hypotheses, and some of the speakers as we go along will talk about this in a little more detail. So I'll let them move on to them now.
No, that's perfect. All right, our next panelist is Rob Runkle with the U.S. Geological Survey. Please join me in welcoming him.
Hello, everybody. I'm really happy to be here tonight. Thanks to Heidi and Fort Lewis College for having me down. I've been a really lucky guy in that since about 1995, I've had the privilege of coming down to Silverton and this part of the state to collect water quality samples for the U.S. Geological Survey. I'm a research hydrologist. One of the things that we started doing in 1995 was coming down to Silverton and doing these mass loading studies, much like Joe just alluded to. And it was part of the what was called the Department of Interior Abandoned Mine Lands Initiative. As many of you know, there's a lot of federal land, U.S. Forest Service land, and Bureau of Land Management land up in the Silverton area. And the idea was for USGS and other people to help out these agencies, try to come into the watersheds and really target the worst sources of contamination for cleanup. As you know, there's not a lot of money available for abandoned mine lands cleanup. And it doesn't make sense to go after sources that really don't have much effect on water quality. So we did a number of tracer studies and synoptic studies, they're called, on the various streams in the Silverton area, Mineral Creek, Cement Creek, the Animas River itself. And those have been published over the years. Brian Kimball was someone I worked with over the years. You may be familiar with his name, and Katie Walton Day as well. All right, so just a quick overview of what I'll be talking about today. First, I'm going to go over some just kind of basic water chemistry. The reactions that take place as you go from the headwaters up in the Silverton area where the water is very acidic, and those reactions take place as that water comes down and the pH increases as you move downstream. And so I'll just kind of go through the series of reactions that result in the metals being associated with the iron particles like Joe was talking about, and just kind of give you some background on that. And then I'm going to talk a little bit about pre-Gold King conditions. In October 2012, we did a synoptic study that started at the very headwaters of Cement Creek and went all the way down to the stream gauge below Silverton on the Animas River, known as A72. And then we also sampled a few samples as far down as Baker's Bridge. And then the third part of this talk, I'm going to talk about post-Gold King, just I think 1 or 2 slides on some data from after the Gold King event. By now you've probably noticed that these pictures under both part 2 and 3 are identical. These are a number of natural and mining affected sources in the Silverton area. And the point here is that these sources have been contributing metals and acidity to the Animas River for decades. And they were before Gold King, and they were after Gold King and during. All right, so here's a slide. This is from the Snake River by Keystone. And I always say this is geochemistry at its best because you barely need to get out of your car. You can pull up to this culvert here. And on the far left is the Snake River. That picture shows the confluence of the Snake River and Deer Creek. So the Snake River is a naturally acidic, metal-rich stream. There's really not much mining on the upper Snake River. So that's on the left. It has a low pH and high metal concentrations. And then on the right is a Deer Creek, which might be a stream that Coors would take their water from to make some beer. So it's very clean, has a neutral pH. So if you actually get out of your car and walk at the upstream end of that culvert, those waters come together. And so in this center picture here, on the left is the iron oxides on the bed of this metal contaminated, or naturally metal-rich stream, the Snake River. On the right is Deer Creek. And in the middle, what's happened is that the acidic water from the Snake River has mixed with the neutral water, and the pH has gotten up to around 4.5 or 5, and what you see is a bunch of aluminum. That's that white strip down the middle. So then you walk around the other side of the car, and downstream end, there's white all over the rocks. The water's mixed together, and the pH is higher. So these are the kind of reactions that are happening. A little more detail on that. This just kind of shows that what happens. Let's say you have a beaker of acidic water and you add some base to it. But it also is what happens as acidic tributary like Cement Creek is quite acidic. And then as clean water comes in, the pH gradually goes up. And as more clean water comes in, as you get down towards the Durango area, pH goes up even higher. So the sequence of reactions is shown here. So generally between 3.5 and 4.5, you have iron oxides on the stream bed. And that's the precipitation of iron that happens at those low pHs. So Cement Creek, for example, has a really orange stream bed, but the rest of the metals are still in solution. If you get a little farther downstream, pH 4.5 to 5, you start to get aluminum dropping out. And then finally, if enough clean water comes in and you get pH high enough, things like cadmium and copper absorb onto that iron. So the watershed picture here kind of shows the same thing. You might have the mother lode up there in the left-hand corner. Some cleaner water comes in. You get the aluminum precipitation. More clean water comes in. You get rid of your copper and cadmium. But the big thing for fish is that zinc is really hard to get out of the water. So farther downstream, you have dissolved zinc. Not a big deal for humans. You can pop a one a day and you're on your way. It's a good deal. But for fish, zinc is a bad deal. All right, so that's kind of the basic reactions, and we can talk about how that relates to Gold King as we go through the night here. But Heidi asked me to talk about a couple complications and additional things to consider. The data shown here is hourly data or a time series of data from the Animas River above Cement Creek. And the plot on the left is the pH over this about 24-hour period, and the plot on the right is zinc. And I won't get into the details, but at these particular pH levels, what happens is that the photosynthesis by plants actually affects the stream pH, and that in turn affects the zinc concentrations. So you get this cycle of pH over the course of the day due to the plants doing going about their business, and that in turn affects the zinc. So this has implications for water quality monitoring. It does matter for things like zinc, what time of day you sample, for example. Another thing I just wanted to touch on, and I won't get into all the details here, but what the toxicity of the dissolved metals is. When you get a lab analysis, it typically tells you how much dissolved copper there is, for example. Well, that's a useful number, but as far as the physiology of fish and the toxicity of the metals, it matters what that copper is bound to. So you can put these data from a lab into a computer model, and it will tell you the different species of metals. So this is an example from Corkscrew Gulch over on Red Mountain Creek by Uray, and they did one of these calculations. And just to backtrack, what happens is copper or aluminum will bind with other metals, but there's also free, unbound copper or aluminum floating around. And that unbound, uncomplexed ion is more toxic. So in the Corkscrew Gulch example here, we have 11 milligrams per liter of dissolved aluminum, but only 22% of that is actually the free aluminum floating around, and the rest is bound up with sulfate. Now, for other elements, hardness plays a big role. Copper will hook up with magnesium or calcium, and that reduces the toxicity. So water quality standards for things like copper and cadmium and zinc are based on water hardness. If there's more water hardness, that buffers it and makes it less toxic. All right, so a little pre-Gold King data. In October 2012, we did this Synoptic study I mentioned. We went from Upper Cement Creek down to Baker's Bridge, and the basic idea was to do one of these mass loading studies to determine what the stream flow is at each location and what the concentration of the different metals is. So we did this Synoptic study from upstream to downstream, or over about a 3-day period. So we're just going to go over a few of the results from that. Basically, the idea is, if you get lucky, you have beautiful fall weather, stream flow is pretty steady, and you can kind of get this spatial snapshot of conditions on that particular time. So we had about 30 stream sites down to A72, a few more down to Baker's Bridge, and we have stream flow at all those sites, as well as metal concentrations and pH and alkalinity. So here's an example of some of the data we have from that effort. This is a plot of zinc concentrations versus distance. So on the far left is Upper Cement Creek, and then we work our way down to A72, which is just below Silverton. And then that red line at the below all the data there is the chronic standard for zinc. So as you can see from this data, zinc exceeds the standard all the way from Upper Cement Creek all the way down to the bottom of Silverton. So just to summarize the results from this study, aluminum, cadmium, zinc, and iron all were above the standards quite a ways downstream, all the way down to Baker's Bridge and the Cascade Creek area. We can also use this same data to determine the load. You multiply the concentrations by the stream flow, and you come up with a load. And like I was saying, one of our objectives in this abandoned mine lands initiative was to go after the biggest sources. So the load tells you where the sources are. I just want to point out a few quick things. What the worst problems are really depends on the metal. So the Red and Bonita mine, which is on the upper part of Cement Creek, this first arrow on the left shows that about 20% of all the zinc coming down was from the Red and Bonita. The next one, which you'll find of interest, is the North Fork of Cement Creek, and that's of interest because the Gold King supplies most of the water to the North Fork, and that accounts for over 40% of the copper coming into the system from the Silverton area. And then finally, another one to mention is Mineral Creek. Mineral Creek accounts for over 40% of the aluminum. So again, it really depends on the metal and where you want to go. The Gold King and the North Fork by no means are the only problem in the area. And then just real quickly, I think it was the week of August 10th, just the first full week after the spill happened, I went down to Silverton and did some of my own work and did some work in conjunction with EPA to help them measure stream flow, for example. We had a guy from Grand Junction come down and help with measuring stream flow. So here's just some data from that period of time, and I just want to talk about that and give an example of some of that data and go from there. So these plots are for aluminum and copper load, and there's 3 sets of bar graphs. The blue rectangles there represent EPA data that was collected between 2009 and 2014. And this is at the mouth of Cement Creek, so it's pretty close to where the Gold King is and where you might expect to see a lot of effect. So if you take that data, and this is all from low flow periods, so we're comparing apples to apples. And and then there's that green line just kind of shows the median number for the aluminum load. And then the orange lines are on consecutive days following the Gold King from 2015 here. And you can see there's a huge increase in aluminum load at the mouth of Cement Creek due to due to the Gold King. And then the third set of plots is if you measure that load way up at the Gold King and then subtract it from the Cement Creek mouth, you get back down to where the data was back in 2009 to 2014. The same thing you can see for copper, and remember from the 2012 study I showed you, the Gold King's a huge source of copper. So as you can see in the copper plot here, there's a big increase as you go from the blue to the orange, and that's caused by the Gold King. And with that, I'll be quiet and take plenty of questions later, but thank you for your time.
Brief announcement, there's still food out there. You can go get some more. We don't want to waste it. Okay. All right, our next panelist is a professor here at Fort Lewis College in the Geosciences Department. This is Gary Giannini.
Thanks a bunch. We're going to move downstream just a little bit and focus more on how sediments move through the system. So Joe and Rob just showed us some good dynamics of the geochemistry, and so now we want to mix in some of the physical sedimentation and where that sediment might end up. And this image is all over the web, and we actually couldn't find out who took it. So if you know and you'd let me know, that would be really helpful. But this is a picture of the meander section of the Animas River right above town. And this is the plume actually moving through that segment. And we're going to look at this picture for a little while, so get used to it. Let me see if I can find a mouse. One of the things that you want to notice is when water moves through a river system like this. I'm a sedimentologist. I've been here 16 years, and I've had the wonderful opportunity to go out and look at Animas River sediments for each of those 16 years with my sedimentology and stratigraphy classes. And we've seen a lot of sediments the color of this bright yellow only here, but only some of those might be associated with mine breakouts, most of them with the oxidation of iron, which you just heard about. So when you look at this fluvial system, there are a couple things. I'm sorry, fluvial is code word for river. Okay, so if I slip there, sorry. There are a couple really interesting things to notice. One is that it's very, very sinuous. Not all of the Animas is like this, but when you hit low gradient portions of river systems, they often become quite sinuous like this and make meandering streams. And these also set up, so for I think you can figure out that the flow goes like this through the slide here. Current velocity varies quite a bit in there, and that controls where sediments are deposited versus eroded in the systems. So this portion this is called a meander here, where the orange is going around. Is that working? You can see my mouse? Okay. And this outer part of the meander is called a cut bank, where sediment is actively eroded from the floodplain. And as it comes around the bend, sediment is deposited on the inside of the turn. That's called a point bar. And current velocities are much slower. So finer grained sediments end up on the inside of that point bar. Let me show you what that might look like. Just a minute. So I've colored in the places where we would expect to have the thickest accumulations of fine-grained sediments. And the Gold King spill sediment is quite different than what usually comes down the Animas River. A lot of us are used to seeing it turn the color of the Hermosa Cliffs when we have flash floods, or after the Missionary Ridge Fire, when we had hydrophobic soils and that flushed in a lot of silt and clay. It usually goes to a much more red color. And it's a very different kind of sediment. That's little clay particles, and those clay and silt, and those actually settle out relatively quickly when you get into quiet water. What we had come down in the Gold King spill was we call a colloid, and that's a much smaller particle and tends to stay in suspension longer, so a lot more of that flushed through the system. But this also means that when we go out to look at the river system here and the river system sediments, that we have areas where we expect there to be higher concentrations of these sediments. And that would be in these slow velocity zones that you see highlighted in this slide. One other piece of work that I've worked on here at Fort Lewis College with a wonderful plant community ecologist who also happens to be my wife, who's back there, Cynthia Dott. And we study the interactions of groundwater in these point bar deposits with riparian forests and the interactions of water in the channels that flows through the sediments that make up these point bars. And that's of interest for this study in terms of how much of the water actually might migrate through those point bars. We have preliminary data that suggest perhaps at the time of the spill we were in a condition where water was actually flowing out of the groundwater into the river, which is really good news. The only bad news would be if somebody here at the glider park had a big well running. That they didn't. I'm just saying if they did. Then we might have pulled some of this in here. So this is really just looking at where we would expect to see some of that sediment concentrated in the river system at a scale of up here in the meanders. And my colleague John Harvey, who just joined us this year in the Geosciences Department, is also a GIS guru. And my go-to guru is on the Ganges River right now, Scott White. But anyway, John put together this map of river gradient for me when I was asked to talk about where sediments would accumulate in the Animas River system. There are a couple important variables, but one of the most important is river gradient. And that is the first order control on how fast the water flows and therefore what size particles it can move. And we put a gold star in here for what is about the approximate position you would have the Gold King mine. This is the confluence of the Cement Creek and the Animas River. But you can see it's a very steep, let me get my mouse going here, a very steep gradient. Anybody who's rafted the upper Animas, this is not news. But it's a very steep gradient stream, so there's a bit of a bathtub ring on there, but not large accumulations of sediment. But when you come into Durango, note that the whole graph goes almost flat. And this area, right, let me get my mouse going again, right here is the area I was just showing you in that photograph with the meanders. And that's because right here in Durango, at the north end of Durango, the river is ponded behind glacial moraines that were 14 years ago. Rob Blair used to like to say that you could put on your skis at City Market North and ski to Ridgeway. But those glacial moraines formed a dam here that really changed the river gradient. And then after you leave Durango, it accelerates again until you get down past Shiprock and the section just before Bluff. So when you zoom out on the scale of where you would expect sediment to accumulate in this system, there's this ponded area above Durango where we have some good accumulation, well, some accumulations are not what we had wished for. And then we would predict less sediment stored in here. There's another dynamic, and that is that the amount of sediment in the system from the Gold King spill is the highest up near where the source was and then tapers as you go downstream. So as you look at this again, even though this area between Shiprock and Bluff, Utah comes down to a very low gradient, presumably we'd already caught most of it in the system up here in terms of sediment, not necessarily dissolved metals. So that lets us look at spatial variation in where sediment would be studied, where sediment would accumulate in the Gold King spill. And the next thing we should look at is temporal. Well, this is interesting. Okay. It's always interesting when you send PowerPoints and then you end up on a different version. But anyway, here's the hydrograph of the river. So this is how much water is in the river measured by cubic feet per second. And then this is the date. It was on August 8th at 10:30 in the morning that the Gold King spill occurred, and about 8 o'clock that night when it arrived in Durango. This gauge is right by the Powerhouse Science Museum. And that little kick right there is about the plume reaching Durango. So one of the interesting things to note is that before that plume ever got here, there had been a series of rainstorms, and we were on a falling water level in the river. And what that means is when the plume came through, it painted the upper part of the bars, the sandbars and things in the river, and then water continued to drop so that sediment became stranded on our beaches. And what you can see across this graph, I put in the level of the spill right here with this dashed line, and it really wasn't until October that we got water as deep as we had during the Gold King spill. So if you saw that sediment around for a long time, it's because our water levels were low. And of course, when this rainfall brought us this hydrograph back up, we all started to worry even more about remobilization. So what you can see is that we're in, on this graph, it's a pretty low flow time of the year for the Animas River. But the next graph shows what happens if we look across 5 years of data from 2010 to current. And the annual peaks you can see here are associated with snowmelt runoff. The secondary peaks are monsoon or late summer storms, and sometimes we even have fall storms like we did in October of 2011 when we saw 22,000 cubic feet of water come down the Animas River, which, no, Ed, did you did I say 1911? I said 2011. Oh, sorry, 1911. If it was 2011, then Dalton Ranch would not be in a good way. Or Main Street. Well, Main Street was, anyway. So what we can expect, and what everyone's most concerned about then, is that we're going to remobilize that sediment again. And we will certainly do it this coming spring and perhaps during the coming years. So that clay-like sediment should be compacted, be turned into chips, and that will be carried along and dispersed on the bottom of the river. It will certainly be reworked off our beaches, except for where it's buried. And then the other interesting dynamic that both Joe and Rob talked about is how much of that will actually dissolve and get going again. And it's really hard to dissolve that material without radically lowering the pH of the river. And that's really hard to do on this stretch of the river. So we would expect that most of those metals would remain bound up as this moves again. The only one that's of greatest concern, we had a speaker that couldn't make it tonight who works on these kinds of systems, Ken Williams, couldn't remember Ken's last name. According to Ken, the metal we'll have to watch the most is arsenic in this whole system. So I hope that gives you an idea of some spatial variability of where this Gold King spill sediment might end up, and a little bit of temporal variability about how we might expect it to move. There you go.
Next one going. So as you probably could tell from our last speaker, we actually have a lot of different scientific expertise here at Fort Lewis College. And I just wanted to encourage you on your way out today, if you stop by the information table, we have different handouts that describe all the different scientists and what they're working on in relation to the river. So next, I'd like to introduce our next panelist, Brandon Francis from Juan College. He's a student that's been working closely with Dr. Kevin Lombard, sampling sediments in irrigation ditches in northern New Mexico. So join me in welcoming Brandon Francis.
I think the last time I was standing in this room was the symposium from the Fort Lewis College, and I think my poster was like right here. And I wrote my senior thesis on the history of Navajo agriculture, how we acquired it, how we flourished with it, and how we lost it, and efforts to bring it back. And that's how I got hired up at the Agricultural Science Center up in Farmington, the New Mexico State University Experiment Station. And I was hired to, there's been a resurgence of local grown produce from up throughout the Animas all the way down to Shiprock. And I got hired to do that. And as you can see, on August 5th, this happened. And this is a picture from August 6th of it rolling down. That's my personal pick. And just a pick of the samples and the signs we saw along. As you can see, Dr. Lombard, he's right there with the blue gloves, taking a soil sample with a soil probe. And he came into the office one day as we were doing our research, and he was pretty upset because all the communities from Durango all the way down to Shiprock had decided to keep their irrigation ditches closed. And just the day before, or the day or two before, Durango decided to open up its irrigation ditches. And Aztec, the community he's from, decided that they were going to have a vote to do the same, to open up their irrigation ditches. So we were, in a sense, in a rush against time to get baseline data from these irrigation ditches, as you can see, before they flushed them with the river water. And in the bottom left is when the EPA arrived. I think it was 7 days after we started taking samples, their contractors arrived to start taking samples along the ditches. And when Dr. Lombard came in that morning, it really struck me because he was like, he was really perturbed about what was going on, especially the vote going on. He was like, it's like, we might as well stop calling ourselves scientists if we don't jump on this once in a lifetime opportunity. We might as well turn in our scientific degrees and just call ourselves academics, because we're not going to learn anything if we don't do anything about it right now, right? And that's why I'm glad to see you guys all here. You guys were planning to do something about it, right? I mean, events like this have happened in the past, you know, but it's like it's technology like social media which are helping us come together and actually do something about it. This was the first phase. For the first 2 weeks in August, we were doing soil sampling and trailing the EPA and GPSing their sites that they were taking soil samples in. So later this December, we're going to go back to all these sites that we sampled when they reopened the irrigation ditches and resampled them to see if there was any accumulation. And Dr. Lombard's hypothesis, and that's who I'm here for, he couldn't be here, he's in Nepal, so he tasked me with this. But I've been with him since the beginning, working on all this, and I've seen all the data. And his hypothesis is that eventually, due to the flow of the irrigation ditches, that sediment will build up, and it will no longer be on the surface, but it will rather be buried. So that's why we're taking these transects and going 18 inches down to establish a baseline for future studies. And here's some of the irrigation ditches. The problem with the irrigation ditches was that there was so little warning, and people weren't used to closing their irrigation head gates in the middle of the season. So a lot of the irrigation ditches got contaminated, because of this. They either couldn't close them all the way, they didn't know how, the people who were responsible for closing them weren't there, or they were rusted up and they couldn't close all the way, or they leaked. As you can see on the far one, and this is an example of a transect, and here's some sludge samples we took in the middle. And here's a sample, and the next month of sampling took place because we realized that each of our samples were going to cost $100. And a transect 18 feet wide, we took samples every 2 feet and 3 samples down. And this came up to over like 300 samples, and we took it to the independent lab, and they're like, this is going to cost you $30,000 to run all these samples. And we ran into that problem. And to fix this problem, we called in, you might have heard about it in the paper, expert from Texas Tech University, David Weindorf, who's a foremost expert on PXRF technology, which is X-ray fluorescent spectrometer gun, which can take field samples right in the field within 60 seconds, within 5 to 10% variance. And this is September 1st, is when we started doing these samples, and these are the sample sites in Aztec and Flora Vista. There's Dr. Weindorf, and as you can see, the X-ray fluorescent spectrometer gun, and you can see his doctoral candidate in the picture on the right. And here's the second day. This one is in Cedar Hill area, where we did there's a lot of alfalfa fields, and in those fields it's where we found one of the highest concentrations, like Dr. Giannini was saying, at the oxbows or meanders. And this data was comparable to data we found further up the valley, like near Trimble Bridge, as I'll show you in a bit. Here's us doing more work. And this is at the student forum, we were talking about the die-off of plants and of insects. And at that site, we found a mass die-off. In every one of these sites, we found mass die-off of bugs. As you can see, in the clay, the dried up clay, the amazing thing about this gun is that you can do wet samples and dry samples. And you can see Dr. Lombard in the bottom collecting plant samples. And what we were doing with the X-ray XRF gun is we're taking controls from places that hadn't been irrigated with the Gold King mine water and using that to compare against data that had from fields that had been irrigated with the Gold King mine data. And where Dr. Lombard is taking his the sample in the picture was this massive gray field or yellow field. And on the third day, we went through Shiprock and sampled there at these sites. The hard part about getting these samples is you have to ask permission to get these sites, personal permission. So that's why you see that they're not clustered together, or there's no site here, 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 there. It's like they're spread apart. It's because we actually had to get permission in each of these sites. So then we decided to go up to Colorado and test this XRF gun in certain spots. And here's one of our findings near Cedar Hill. I just wanted to show the iron level. That iron level is within residential limits. It might look high, but it's within residential limits. The high thing you should look at is the lead. And as you can, and only the lead and the arsenic at the bottom. Arsenic, we theorized that there should be a future study on arsenic because there's inorganic arsenic and organic arsenic, and only one is harmful. So here's what we did to study. Up there in the north, you can see that's by Trumbull Bridge. That was our last sample site. And down below is by Home Depot. And here's the Trumbull Bridge. And as you can see, the lead level is 375. The residential loading limit for lead is 200. So it's way above. And this is at Oxbow or Meander. And this is the last, when we were sampling with Heidi and Callie up at the Callis Hands Ranch, taking weed, plant, soil samples as a part of her study. We wanted to establish protocol, so when studies like this in soil samples are done, we'll be doing the same thing across the board, and there'll be no, and this is basically our findings. Basically what I talked about, and due to the wet season that we enjoyed, we were very lucky that this event happened during this time because most of the sediments washed down, but we don't know the effects of where it's going to accumulate like we were discussing earlier. And the region already has a high history, prehistory due to heavy metal mining and due to natural geologic processes. And the last one, this is what me and Dr. Lombard discussed, like if we want to move forward, this is what we need to do. More XRF studies, a warning system in the advent of a similar event, more monitoring and studies of the arsenic that is present, and sharing of data, and academic sharing across the board. Thank you.
All right, so our final panelist tonight was going to be Ken Williams from Lawrence Berkeley National Labs. Unfortunately, he had a serious family medical emergency and was unable to make it tonight, but he did provide us with his slides, and Heidi is going to share those with us.
Thanks, Kelly. We'll keep this part fairly brief so we can move on to the questions and answers. But I wanted to highlight that the DOE, the Department of Energy, has done a lot of research for a long time on metals and how metals move in environments, and they focused a lot of that research on river systems. The Department of Energy began a large-scale new research project over on the East River by Crested Butte, and that project will be looking at a suite of metals, a suite of other elements, with the aim that if we can understand a watershed well and model it, we can then apply those models to other regions, and such as the Animas, and begin to have some prediction to know what's the long-term impacts when events like this occur. That project got underway last year. This year I was asked to join it, and that's how I met Ken, and I've been working with him this summer. We will find a way to bring Ken here another time. He's a fantastic speaker, and I think that you guys would really enjoy him. For the Animas, I'm just going to share a couple key results from what he did on the Animas. So he came here on the 3rd and 4th of September to do some stream sampling. He worked with myself, with Mountain Studies Institute, and then the samples were sent to the University of New Mexico and the Ohio State University for analysis. He sampled soils, water, as well as microbial DNA. So that was something that you haven't seen people talk about yet. He wanted to know the microbes that are living in these sediments as a component part of what he wanted to understand. The key findings that he has are what you see underneath the photo at Baker's Bridge here, that metals were released to the river primarily as solids, such as iron oxides, rather than dissolved in the water. The accumulation, both accumulation and burial happened along the river corridor, and that's been mentioned by several people so far, that burial means that some of what's there we can't see anymore, and we want to be able to still monitor and pay attention to it. He did studies to investigate the mobility of metals in the system, and those included microbiological studies with the bacteria that he harvested from the system so that he could understand whether or not the bacteria here, with the carbon that's present in our system, and the carbon is a resource that microbes need as a food, does that enable them to convert arsenic from one form that's not that harmful to another form that's more harmful, and Brandon alluded to that. This describes just a little bit more about that sampling. He focused, this is a photo of the Durango area. The BB at the top is Baker's Bridge. The 32B at the bottom is 32nd Street, and a couple sites in between, including the OX, which is Oxbow Park, that area that Gary highlighted as being an area he thought sediments might accumulate. And sediments were sampled at 2 depths and included microbial metal concentrations, and I'm just going to focus on the sediment data. With the data that's shown here, there are element concentrations on the y-axis of these graphs for different elements. The full name of the element is written in the title at the top, so we're not expecting you guys to have your periodic table memorized. Cadmium and zinc is what's here, and there are a couple key things that I want to highlight about a set of graphs like this. This set of graphs, 2 elements, cadmium and zinc, the bars look similar. From one site at the top, for each site, so sites along the x-axis, for each site, when you look at the top and you look at the bottom, you can see those metal concentrations parallel one another. And we expect to see that in some cases, but not in all cases for all elements. So some elements follow one another, some elements don't follow one another. Those are all 3 Oxbow sites. So they're all 3 on that, at this location, right down here. So 32nd Street Bridge is down here, and then that's Oxbow Park, and he actually went out with Gary and Cynthia to do the sampling at Oxbow Park. And they're from different areas, right, all there, but that's a key point I actually want to make, is that they're all right close to one another, and yet you can see that for 3 sites that are really close to one another, they can have different metal concentrations even though they're near each other. So sometimes metals have similar concentrations at the same site, and then you can have the same metal and have different concentrations in very nearby areas. And that highlights the challenge we have ahead, which is to do what level of sampling is needed for us to properly understand what's here. The next is to switch to a different set of elements. And for this one, you can see that it's copper on the top and lead on the bottom. And for same sites, you can see differences. So you can see that Baker's Bridge is high for both of these, but there's more or less variation within those Oxbow sites, depending on the element that we're looking at. Gary highlighted Baker's Bridge. Baker's Bridge wasn't high for cadmium and zinc. That's the BB site. But it was high for copper, it was high for lead, it was high for arsenic, and it was high for mercury. And so there's also the possibility that as part of the way that the sediments moved into the system, that there are some locations where we want to make sure we spend a lot of time to understand them better, because we can see a pattern of several elements that have accumulated in those sediments at the same site. And there's again a photo of the Baker's Bridge. And the final point to make is related to the arsenic. So with the the bacterial present from our watershed, from our sediments, the carbon that was extracted from those sediments, and the elements that came from those sediments. They've set up laboratory incubations to see whether or not the bacteria are the right kind of bacteria that can take arsenic from a less harmful form and move it into a more harmful form. And the initial results from that experiment suggest that the right bacteria are present to do that. And so as Brandon noted, it's something to have on our radar to pay attention to and to start to understand the arsenic chemistry more as part of what came out of the watershed. With that, I think Callie's going to transition us to the panel.
All right. We're running about 10 minutes behind, so we're going to shoot to finish up at 7:10, but that gives us 30 minutes of Q&A. So I'm going to invite all the panelists to come take a seat up here while I'm figuring this out. Okay. I also invite anyone with questions to line up at one of these two mics. We're going to just alternate between the two. So if you have a question, please come approach a microphone. And once all of our panelists are seated, we'll start at this mic right over here. So go on ahead. Thanks. Oh, on switch. On switch.
You switch.
Thank you very much for your presentations, and I was just wondering if any of the panelists could give us recommendations related to dogs in the river. For instance, over at the dog park, a lot of great technical information, but I couldn't interpret it in relation to if I should be worried about my dog, the sediment, especially where I see orange, that sort of thing. Thanks.
So there's not a lot of data available on the toxicological effects of these metals on dogs. So what I was hoping with what we presented is an opportunity that we can start to understand what metals are present and where and how we learn about how much is there so that we can develop a system that we could use to inform personal choices for whether we go in the river and how often we go in the river and how often we have our dogs in the river. The maps that were running when you first came in, those were maps made by students at Fort Lewis College using EPA recommendations for safe levels of metals that are determined for people. But a lot of the way that we have legislation available, we have guidelines for people, but not for pets, unfortunately. And then the use of the river by pets is going to be very different than the way people use the river.
I appreciate you all. I have a combination question. A number of people we know have seen spikes in barium and nickel in the river. And there's some complex scientific possibilities for that. I wondered what the test baseline was on the periodic chart for all metals and all daughter-in-laws. Were any testing done for daughter-in-laws?
Let me ask for just a bit of clarification on that. You're interested in detection limits? Is that what you meant by?
Not only detection limits, but is only the Clean Water Act study being utilized, or is it a full spectrum metal study for the water and for the sediment?
Yeah, I don't know if any of us have a lot to say about that. We don't have a lot of familiarity with the post-Gold King data. I mean, all I will say is that I know nickel hasn't been an element of concern for aquatic life. For example, that 2012 data set I was talking about, nickel did not exceed the aquatic life standards.
There are some medical scientific standards, though, for human exposure for nickel. They're not ATSDR. The only other question was, I wondered if any of these metals can filter through the domestic water treatment systems here. Micron size and those kind of things.
Most of our water treatment systems, actually, it's quite interesting, use some form of coagulation to remove various contaminants. And one of the the typical technique for that is to add some form of aluminum or in some cases iron, much like was present in the river that kept a lot of these metals attached to particles. And the goal in water treatment would be these particles would settle out. They'd be quite effective at taking metals with them. Of course, the water intakes were shut off on top of that, but any residual that might come in the future, the expectation would be our conventional water treatment systems would be highly effective in removing typical metals.
Excuse me. As a follow-on to the last question, for someone who's on a well that's right next to the river, can you give us some idea of, how it will filter through the ground to the groundwater and what the likely effects of that might be?
I think first of all, it is a concern. One should make some assumption that's going to be some connection between the groundwater that's coming into your well and surface water, although people don't always make that connection. The second thing would be that a good example to draw on in this case is over the years, water utilities have used that very kind of a system to help them do a better job at removing various contaminants. The technique in water treatment would be to do bank filtration, and the whole idea of the water moving through the sediments between the river and a well are thought to provide additional removal mechanisms. The question would be, when you get down to details, would that be effective for every metal that we've encountered in the Animas and further downstream? Would there be any changes in the geochemistry that might make some metals more mobile than what we might expect? And I think that should be a topic of concern. It should be a topic that some extra monitoring is done for those kinds of systems. It's not something that we could necessarily make a definitive prediction of in all cases for all metals.
Do you know if any work is being done in that area in terms of studying the likely future effect?
Here in the Animas, is that a specific question too? So what I'm aware of is that groundwater or home wells are being tested, and that's something that the EPA has been covering with tests. The big new study that is starting over on the East River does include groundwater, and it also, the emphasis and a lot of the expertise that the Department of Energy has is in how those metals change in soils, both due to physical processes, chemical processes, and biological processes. And they are doing sampling with depth and sampling of microbial communities with depth and sampling of the groundwater. That particular project's at the beginning stages, and so, what we learn there could inform what we understand for our region and our community. The other studies that they've been doing have been focused at Rifle and along a floodplain area in Rifle, Colorado, and those have also focused on groundwater and how is groundwater affected. And that particular study site was chosen because it was an area where there was waste from previous Department of Energy activities. So I think some of that knowledge is out there about how the system works, and one aim would be to bring that knowledge to our community. I think Ken could have done a really great job answering your question.
I'll add just a little.
Yeah. Go ahead.
I'll add just a little bit to that. One issue is obviously how far your well is away from the river itself. And, one thing is, as Joe mentioned, most of the contaminants would be in solid form, and that would be filtered out, even if it did make it as far as your well. But the other thing to keep in mind is that the Animas River is generally gaining water. There's tributaries coming in, and so the direction of flow is probably towards the river. If you were pumping enough, you would draw the water table down and potentially pull some of that water towards you. But again, it would likely be filtered. And I guess the other thing to mention is that, if people do have their wells tested, in most cases, you're not going to have a pre-Gold King sample from your well to compare it to. So that may or may not, be caused by the river. Could be the natural groundwater, you don't really know.
But one thing we've heard in a number of these talks is if you're going to watch for one element, watch for arsenic. At least that's the one that we anticipate there would be the most potential mobility.
Hi. Thank you. I really appreciate all your scientific research, and I have a very non-technical question. Can I take my nephews to play at the Oxbow Park in the river this summer? Okay. So basically that's my question, but I live across from Oxbow Park, and we play in the water from there all the way up to the Iron Horse, and I rode my horse on the banks today, and just a lot of orange sediment and sediment in the river, and really bright green still. And how safe is that? And is it not a good idea to be playing around that area in the spring when everything is going to be flushed back into the river? I mean, I know that everybody said it's safe to go in the river, but I was wondering if that's more like below 32nd Street than it is above.
You want to do your environmental toxicology thing?
So it's not an easy question to answer, although I can appreciate asking the question. I'm still asking the question myself too for my young kids and making choices. One of the things that I feel like we need to do more of, and I hope that an opportunity like this forum creates, is that we're learning from each other. I've learned a lot from these the talks so far and what I've learned from my colleagues, and we need to do more monitoring. I mean, that's what I keep getting a sense of, is that I want to know more about what's there. I'd like to know more before the snow melts, before the snow comes and the snow melts. Because that'll already start to give us an idea of how much the flushing event of snowmelt that Gary describes moves things out of the system. And then it's possible that we could develop something, and this is in sort of recommendations and conclusion ideas I had for this forum, is akin to an avalanche report or a snow report, where we could, with good monitoring data, provide people with a gauge of should you be concerned today or should you not be concerned today. But ultimately, it comes down to choices that we make about the risk. Generally, the system is not that risky, is my understanding from what I've heard and seen for comments and discussions today, including the forum we had earlier with stakeholders. But ultimately, we're all making a choice. It's not a no metals environment, but it wasn't a no metals environment before this spill,
Right.
if that makes sense. And so we just need to try and help to get to where we know what's there, and then compare that to EPA standards and develop a system where people can easily do that on their own, so that you don't feel like you're struggling to make a choice without information. We'd like you to be making a choice feeling like you can, because you have the information you need. And it's going to change over time. And so that's why we need to keep doing monitoring.
So is it safe to say if the water you're playing in is orange, or the sediments on the beach are orange, you probably shouldn't be playing there?
Yes.
Oh, thank you. Thank you.
I mean, if your nephew puts that orange, that's true. If your nephew puts that orange material in his mouth, as some
Not good.
small kids do, that would be not great from what we're seeing, because that would go into his stomach where the pH would change and lower,
Okay.
and then the metals would be released.
Well,
So don't eat the orange
Yeah,
stuff.
and I really appreciate this. I know it seems really simple, but everybody said go in the river, it's safe, and on a lot of us up on that and that side of town are just like, it doesn't look safe.
Well,
It's orange.
Recall in what I showed you is that we've only just gotten that wet a little bit, right? We've had flows back up to the level of the spill, but we haven't had the scouring flows that we would expect in the spring. And so after spring snowmelt, there'll still be some of that orange sediment left behind, and that will still have a lot of metals in it, but there should be less. As for the green, that's algae, and thank all your upstream neighbors who use fertilizer.
That's great, thank you. Oh, sorry, you guys.
Hello. So I know Ken wasn't here, so maybe you guys won't be able to answer this question, but I am interested in that bacteria. Oh, hello. I am interested in that bacteria that converts arsenic to the more dangerous form. Is that kind of like a slow-growing bacteria? And does, like, when they convert it to arsenic, is that kind of like a slow process? Is this something we're gonna have to be worried about rather soon in the future? Thank you.
Yes, sorry, Keisha, that's a great question, but I don't know enough about the bacteria other than to know that for some bacteria you can't culture them in a lab, so it was interesting that he was able to do that.
Hi. I see a lot of people that are doing studies now, either on geology or chemistry or stuff like that. One of the key things, we can monitor and we can see what the levels are, but what I don't see is anybody going to be doing any risk assessments on uptake, because what we see for a standard in EPA may be for an exposure over 24 hours or something like that, but it's different if you're going in and swimming for an hour and then you're out of there. So is anybody doing that kind of studies where they're going to say, this is the risk if you're swimming, this is the risk if you're boating, this is the risk if you're just walking by it, or just walking on top of an orange-colored rock? And then you're going home for 2 weeks before you do it again.
So we heard from, where are you? You're in the crowd. The EPA standards. Was it the other session? You want to talk to this?
We did make sure that San Juan Basin Health was present.
Right. So here's a little bit about how those are established and how many hours you can spend in the water, or an assessment of risk based on how long you are in the water. So here you go.
Hi, everybody. I'm Brian Devine. I work at the San Juan Basin Health Department. We're your local public health agency here in La Plata County. And I felt compelled to come up and offer a few clarifications from a public health perspective. I heard some questions earlier that I'll address first, asking, can I go in the river? Can I let my kids in the river? And at this point, the health department's recommendation is, yeah, you can. You need to exercise some common sense. If you emerge from the river covered in orange sediments, you should wash them off when you get home. When you exercise in river water, when you go swimming, when you go boating, we think you should wash with soap and water when you get home. This is a recommendation that we would have made before the spill. This is untreated river water. It's had metals loading for a long time. It has nutrient loading, as we've described. This is a recommendation we would make before the spill. After the spill, it's probably a recommendation we'll be making 100 years from now if we're still around as a department. The standards that are in place, there are kind of two of them. One is a long-term exposure standard. This is for sediment. One is a long-term exposure standard. One is a much shorter-term exposure standard. So obviously, you would have to be exposed to a much higher concentration of metals over a shorter period of time in order to have some kind of health risk. The sediment sampling that's been done is pretty rigorous, but as you've seen from some of the results, it's highly variable, even in a small location. So we're probably not able to capture 100% of the variability in metals concentration in sediments. But that being said, only at about a dozen, maybe a little more than a dozen places up and down the river has the EPA or the state found sediments that are in excess of, and I got this wrong earlier, but I did my homework this time, about a dozen places where the sediment was in excess of that long-term exposure standard, what we call a residential exposure standard, which is obviously much lower than a short-term exposure standard. The residential standards, and they're actually not even standards, they're not legally required to be met or anything like that. It's just a screening level for evaluating your health risk. At about a dozen places, maybe a little bit more, they've been in excess of those residential standards, which is based on ingesting 100 milligrams, which is about half of your normal ibuprofen tablet, about 100 milligrams of sediment at that concentration every single day for 30 years. We've had about a dozen places where some metal has been in excess of that standard. Well, as you'd expect from the slides, they're more concentrated in those low gradient areas in the North Valley. I don't know the specific sites. The data is available. You can look through those. Frankly, it's not always presented in a very accessible way, but the data are available to know exactly where those are. At none of those locations, at none of the locations sampled by the state or by the EPA, has the sediment been in excess of those short-term exposure standards, which is based on, again, ingesting about 100 milligrams of sediment 4 days a week for 16 weeks. And that was based on sort of a conception of what your recreational exposure might be to sediment if you were using the river for recreation sort of regularly throughout the recreation season. So I want to stress that yes, there are sediments that might cause an elevated risk of health concerns if you were exposed to them very, very regularly for 30 years. But also, as we've seen, we don't really expect those sediments to be around for 30 years based on the water level when they were deposited. And none of them, where we sit as the health department, none of them are concerning from a short-term perspective, from recreational exposure. And so our advice really at this point is common sense. Supervise your children when they play in and around the river, because as Gary said, sometimes they do like to eat colorful things. If you are playing or recreating around orange sediment and orange water, or even if you're not, quite frankly, it's a good idea to wash with soap and water when you're finished. That's a good public health practice, regardless of the state of the river. And there are similar standards for the water column as we have for the sediments, also based on that 4 days a week for 16 weeks of exposure. And during the plume, some of those were exceeded. But now, daily sampling results up and down the river since then have indicated that none of those are exceeded. So from the health department, our recommendation really is just to use some common sense, to supervise your children when they play in the river. We had a question about dogs earlier, and we don't really know as much about toxicology in pets as we do in humans. But again, if your dog emerges from the river a much more orange color than your dog was previously, we would recommend that you wash your dog. And we think these are common sense measures, and we think if you follow them, we don't expect that there's any elevated risk of health concerns from recreational use of the river. And I hope that answers some of your questions.
Thanks, Brian.
Thanks, Brian.
Yeah, Brandon, you mentioned insect die-off. That's the first I've heard of any kind of animal life die-off. Has that been witnessed anywhere else except down? It would seem to me that would be more of a problem upstream than downstream. I have a couple other things.
The main problem was like at the meanders and oxbows, we would find situations like that, but it was mostly flies.
Background vertebrates?
Yeah.
Okay, and well then, you described how arsenic gets mobilized through bacteria, that's really interesting, but what are other mechanisms to mobilize the sediments to pose a hazard to background vertebrates, fish, or higher life? Is that something we need to worry about?
One area we were worried about was the accumulation in plants because the defense mechanism for plants is to hyperaccumulate or heavy metals as a defense mechanism. And this is especially prevalent in grass species and brassica plants.
And so that'll be uptook by cows or deer or
Cows, deer, humans.
Is that a big risk?
Oh,
or we don't know.
We have no idea.
Great.
Yeah, and you had asked about remobilization of the sediments. Certainly when floods happen, those sediments will move downstream and so forth, but as I was kind of pointing out in my talk, the effect of pH is for the dissolved concentrations to go to solid concentrations as the pH goes up. And so as long as the pH is neutral, those metals are going to stay bound to the solid particles.
Well, except for arsenic.
Yeah, arsenic's a little bit different.
But that doesn't apply to any of the rest of it.
No.
Thanks.
Hi, I was just wondering, there was a slide towards fairly early on in this presentation that was talking about how different metals are more toxic when they're in their free ion form as opposed to when they're in a complex. And I was kind of wondering what types of environmental factors can impact that ratio of how many free ions there are as opposed to being inside complexes.
Yeah, it's mainly the water hardness for the metals that are coming down from the Animas, the calcium and magnesium. So when the water quality standards are calculated, for example, you have to consider what the water hardness is. So, you know, hard water is not good for your laundry, but it's good for complexing those metals and making them less toxic.
And then also, you talk a lot about, just in general, how pH affects how much a metal can dissolve in the water, and what other factors can impact that, like temperature and...
Well, I did show those, and it was a pH effect on the zinc concentrations, how they vary over the day, but there's a thought that temperature also plays a role in that. Basically, reactions happen faster when it's warmer. So you might have more absorption and lower metal concentrations during the hotter parts of the day, and higher concentrations when it's cooler.
But it's just pH is like that most impacting, I guess.
Yeah, I mean, Joe teaches chemistry to grad students, but I was taught pH is a master variable. It controls the metal concentrations.
We have time for about 1 or 2 more questions, but we can continue on the way out the door too. So you can go ahead.
Thanks. Hey, I was just wondering how the community can continue to help with this process of figuring out what the effects of these spills are, and how we can stay informed. And
I feel like that's what I have for my conclusion, so maybe we'll ask one more question and then I'll conclude, and then we can finish the appetizers that are outside. So why don't we do one more question and then I'll answer your question, Aaron.
Ladies first. Go ahead. Do you have a question?
Yeah. Yeah, it's hello. My name is Markel Vigay, and I have a question for you all, to any of you. If you would happen to know of any current remediation projects occurring in result to the Gold King mine spill? Could be water or sediment.
Well, one of the things that's happened, prior to the Gold King blowout and kind of flash flood from that, the Gold King mine was discharging between 100 and 200 gallons per minute. And then after the initial burst, that discharge rate went up to 600 gallons per minute. So because of that increase, EPA is actually contracted with a company that's built a small treatment plant at the Gladstone area, about 8 miles upstream from on Cement Creek, up from Silverton. And so that's, I was up there a couple weeks ago, and I think it's close to being online, but they've been treating water in some form by raising the pH since the initial Gold King incident. The other thing that's going on up there is that was in the works before the Gold King happened was the idea of plugging the Red and Bonita mine, which is fairly close to the Gold King. And the idea would be to plug that mine, let the groundwater level fill up to kind of pre-mining conditions. And by plugging the mine, the idea is to shut down decrease the rate of oxidation, and thereby decrease the generation of acidity and metals that are coming out. So even if the water behind that plug were to seep out other places, it should be of better quality.
Thank you.
Also, thank you very much for all your time and being here and putting all this information in front of us. I'm still trying to interpret it, figure out what this means. But hey, Brandon, real quick, would it be possible to get a copy of the sampling testing you did at the Home Depot site? Are you sharing that information yet?
Yeah, just give me your email or
Okay,
your
I'll
contact
catch up with
information.
you afterwards.
Yeah.
Thank you. My question basically is in reference to impact of the river water on ag, trees specifically, fruit trees. I just, as a contractor, built 2 large infiltration galleries, one in the river, one just off river, 2 miles below Home Depot. And fortunately, we had not set the pumps, and we were just getting ready to set the pumps and turn on when the gulking happened. But so we decided to wait, let the river at least flush one time. But do you, at this point, I know it's early in the game, do you have any feel for impact of the river quality, the water on ag? I know generally speaking, the thinking is that it's okay.
Yeah.
Isn't that?
So my general thinking is that the Gold King mine spill wouldn't have impacted ag in this season. We don't have the data that we can know the answer to that question, though, because I've been asking around, and we can't find any pre-spill heavy metals concentrations in produce and agricultural products from the valley. So there have been farmers that have contacted Fort Lewis College to ask about where and how we could contribute, and the best approach is to start sampling, and to start sampling so that we at least have some data this year, because it made me nervous to call next year baseline, because it wouldn't be in the year of the spill. So with a relatively short window of time, Callie Cole and I, coordinating with Kelsey Berg, a student here at Fort Lewis, we sampled 4 farms. If you'd like to have us come sample your farm, we're still willing to go sample more farms. What we're sampling for are fruits, roots, and leaves that you eat. So we're trying to get different parts of the plants. And then we're also collecting weeds. And weeds because as soon as you switch a crop species, you're going to have different concentrations because it's a different species, and different species accumulate metals in different ways. But for the weeds, they're everywhere, and we can get a really good spatial perspective. And one of the farmers was the one who actually contributed the idea that we should sample bindweed. Bindweed has, it's everywhere, it's throughout the valley, it's got roots that go to who knows where. It is actually a species that does accumulate metals. And so we're looking into setting up maybe for next summer, We'll Come Weed Your Gardens project. Yeah. And we'll start collecting some weed from around the valley. The bindweed weed, not the other kinds of weed. I do realize I just said that. But it's getting late. And then we can start to know. We're also we're gonna compare that back to data from other systems, like what are normal, what are different values compared to our valley, and then we can look forward to see if we know something better for the future. If anyone has old corn cobs in their garages that they haven't got rid of, we're also interested in old stored plant parts.
For baseline studies.
For baseline data, yeah, because it doesn't deteriorate with time. So people's older agricultural products that are still in their garages would help us.
Of course, the point of all this is try to figure out what's safe and what isn't, kind of on food, on ag, to drink, eat, all that, right, to play in.
Yeah.
And do you see a point in the future? I mean, you willing to guess a couple of years maybe we might be better armed with information to start making some calls?
Yeah, absolutely. And with that, I'll answer that question that you just asked, and I'll answer Aaron's question too. I have a mic up here, so I'll use this one. So the questions you've asked, the issues, are important ones that Fort Lewis College shares with the community, and we'd like to see how we can help address. This panel forum that you've been a part of has been videotaped, and it'll be posted on the Fort Lewis College YouTube channel, so we encourage you to share it with other people that you think may have an interest. And it also gives us an opportunity to slowly review information, because we know there was a lot of information. We hope that there was at least some redundancy across the different talks, so that if one person wasn't clear about explaining how pH affects metals and metals in solution, then maybe we were able to communicate that well through another person's talk. What I wanted to do was highlight a few ideas and recommendations potentially for moving forward. So where and how can the community be a part of identifying and planning for how we understand things? The first step is that we need to do more monitoring, and I think that's been highlighted by several of the things that people have said. We want to monitor agricultural products, we want to monitor metal concentrations in groundwater, well water, we want to monitor metal concentrations in the river and in the sediments. Those analyses take more time, they cost more money. There are other things that we can do really cheap, such as pH and cloudiness or turbidity of the water. And so we want to do some of those things that help us to understand how the system works and where the metals could be, even if it's not monitoring the metals themselves. And that was part of why I had folks present some of that background chemistry for you all, is to know that when people are monitoring pH, turbidity, measures like conductivity, how much salts are dissolved in the water, we're getting at and we're able to understand some of these other issues related to the things that we're concerned about. I also want to emphasize that daily data is really important. That when we take a measurement every day at the same location, year after year after year, we start to understand how the system works better. And that basic understanding of how the system works can help us understand past problems, future problems, and how to manage for those problems. And so currently there are a lot of groups within our community, nonprofit organizations, government agencies, that are working to see where and how can we plan for doing more monitoring and to get the community involved in doing that monitoring. The second step is clearly informing. Hopefully this will be the first of many different types of forum that are offered by the community, ones that are offered by Fort Lewis, ones that are offered by other organizations in our town, so that the information on the monitoring is available. There's the possibility that we can develop some kind of a system where, just like a snow report, you can look at the data on the river daily. We look at stream flow in the river when we make decisions about boating, and what Brian's suggesting from San Juan Public Health is suggesting to you is that we would just add another characteristic of what we look at for the river and that we take into consideration. It may feel like some of the data you want, some of the knowledge you want isn't available yet. It's because it's ongoing and it's in process. We had a flag waved in front of us with the Gold King mine spill this summer. There's a certain level of understanding of the system we have. There is a certain additional level of understanding we need to gain, and we're working to gain that. And what I'd like to see us doing is doing that as a community. I'd like to, the same way that I engage my students in the process of science, just through going through a student, a professional stakeholder, and now a public forum, there are ideas you all have contributed to the group of us that are here, that, and folks, stakeholders that are in the audience, that we could start to plan differently for monitoring, because we can hear what people want to know more about. If that makes sense, we're not always going to make the choice first in front because we're thinking about things in a different way, but by having a discussion like this, we can start to think about what do we all want to see monitored as a community, and we can start to plan for that. So I appreciate and thank you guys for the ideas that you've generated tonight for what we need to move forward with. One of the primary aims of tonight was to provide the science needed to understand the data, to help with phrasing questions, with understanding the context. With understanding the context, this is a high metals environment. It has been and it will continue to be, and what processes influence when metals are. There were a fair number of questions about health risks, and some of that information is already available as fact sheets that San Juan Public Health has put on their website and is available. And then and they're over here on the left as well. And then we really appreciate Brian being here so that he could answer some of your questions as well. And then ultimately with the information and the monitoring, we're choosing. We're choosing as a community what the risk is that we're willing to accept. We're choosing as individuals what the risk is that we're willing to accept. And that the opportunity to have more monitoring can inform decision managers to potentially reduce the risk at the scale of the watershed, to lower the risk that each of us are experiencing that we don't have control over. And with that, I'll highlight that we can all be a part of the science. I really appreciate you all coming out here to a very science-y forum. My children take part in learning science. I took them to a science research station, and they lived at 9,600 feet, measuring and sampling things in the environment. And there are numerous organizations in town, different nonprofits, that are going to be looking for you guys to be involved as a way that we can get out there and we can do more and we can measure more and we can understand more about the system. We'd be glad to answer questions, and I think there's still a little bit more food out there if anybody wants some. Thank you for coming.